In the previous lecture, we looked at an introduction to neural networks, and we ended with looking at linear separability. In this lecture, we're going to look at a particular architecture, namely the Perceptron neural network architecture. And in addition to that, we're going to look at the Perceptron learning algorithm, which can be used to determine the weights and biases for the architecture. So your Perceptron learning algorithm, together with the Perceptron architecture, performs classification. When we're dealing with neural networks, they can perform classification, or they can actually perform pattern association. Next week, we're going to look at the Hopfield neural network, and the Hopfield neural network performs pattern association. The other thing that distinguishes your Perceptron learning algorithm from the other, the Perceptron architecture from the other architectures is that it's a feed-forward neural network. So if you remember from last week's lecture, your neural network is made up of a number of layers. Your first layer is always the layer that has your input nodes representing the input to the problem. And your last layer is your output layer, which is your activation layer, is the layer that produces the output for the neural network. And you can have hidden layers in between. So if your neural network is feed forward, it's actually moving from your input layer through the output layer through to the output layer when it's learning. And the weights are being propagated from input through to output, and that's how it learns and updates the weights and the biases. Alternatively, you could use a recurrent neural network, and in a recurrent neural network, the output that you get is fed back into the neural network in some way. So those values get propagated back in the opposite direction. So last week we spoke about linear separability, and linear separability helps us decide whether we should use a single layer neural network or a multi-layered neural network. So your Perceptron neural network can be single layered or can be multi-layered. If your problem is linearly separable, then you can use a single layer. If it's not, then you'll have to use a multi-layer. So when we train, you know, with supervised learning, which we looked at last week, you normally need a training set, and the training set is made up of a number of different instances. And training essentially involves determining your weights and determining the bias. So we spoke about the bias last week, and a bias usually has an input value of 1. And depending on the inputs you have and how these are mapped to your outputs, you have a number of different weights for that neural network that you need to train. As we discussed in last week's lecture, the learning algorithm is used to determine the weights and the bias, and the learning algorithm normally runs for a number of iterations. So where the learning algorithm actually learns from is the set of training instances that's provided. So the learning algorithm usually goes through each set of training instances at least once. The iteration through each training instance is referred to as an epoch. Now, usually when you go to the training instances and you find that the output of your neural network with the given weights and bias is not the same as the target output T in your training instance, then you go and update the weights and you go and update the bias, and that's where the learning happens, and you use learning rules for that. Now, if you come to a point where for every instance in the training set, there's no change in the weights and bias, which means for every instance, there's no difference between the output from your neural network and the target value in that instance, then we know your algorithm's converged. So in order for your algorithm to stop, you need to actually get convergence. So if you look at classification from last week is a supervised learning process, and you usually have an input part of your data instance and a corresponding output. So with classification, each entity has a set of attributes, and based on those attributes, that entity belongs to a class or does not belong to the class. So your input vectors for each training instance consists of -1s and 1s, or -1s and 0s, representing the attributes of the problem. So each instance in your training set has an input vector, and it also has an output vector. So the output vector represents, in this case, the class. So that could be represented by a -1 or a 1 or a 0 and a 1 if you're looking at binary representation in binary classification. You can represent your training values using binary, so zeros and ones, or alternatively, you could also use bipolar. With your bipolar, it's basically the same thing. The only difference is that your zero is now -1. So let's quickly look at an example to put everything in context. So the example that we're looking at is one of binary classification. So essentially, you've got a conveyor belt that's in a fruit warehouse. And the purpose of the conveyor belt is to separate different fruits. So you may have apples, you may have oranges, you may have pears. And as the fruit come to the end of the conveyor belt, they're put into different boxes depending on what fruit it is. So the conveyor belt has different sensors, and the purpose of the sensor is to actually determine attributes of the fruit. So the three main attributes that the sensors, there's one sensor for each, is the shape of the fruit. So the fruit can be round or it can not be round. The texture of the fruit can have a smooth skin or it can have a rough skin, and the weight of the fruit. So the weight can be less than or equal to 0.5 kgs or greater than 0.5 kgs. So if the shape is round, then we represent that as a 1. But if it's not round, then we represent that as a -1. If the texture is smooth, that's represented as a 1. And if the texture is rough, it's represented as a -1. And similarly, if the weight is less than or equal to 0.5 kgs, that's represented by a -1. But if it's greater than 0.5 kgs, that's represented as a 1. You could choose 1s and -1s you could do it the other way, that would still be correct. You just need to make sure that you're consistent. So if we look at an orange is round, so the first attribute value for shape is 1. The texture of the orange is rough, so the second value is -1. And an orange weighs less than 0.5 kgs usually, so the last attribute value is -1. Now again, we're doing binary classification. So one class will be represented by a -1 if we're using bipolar values, and the other class with the 1. So in this case, this is a -1. The reason we've just chosen it to be -1. And the other fruit we're going to look at is an apple, and that we've represented that class as 1. You could have them the other way around. That's also fine. That will also work. So now if we look at an apple, the apple is round, so its first value is 1. It has a smooth skin, so its second attribute value is 1, but it's usually less than 0.5 kgs, so its last attribute value is -1. And as it's the second class, we're just representing apples using a 1. So one thing that helps when you've got to work out what the weights are for your neural network is to actually draw the architecture. So if we look at the architecture for this neural network, so here we've got a single layer. We've got 3 inputs, P1 through to P3, and we've got 1 output, T. The bias always has an input of 1. So if we're mapping your inputs to your output, so you've got 3 weights, W11, W21, and W31. And if we look at the weight matrix, that's basically what's going to be our weight matrix. It's a 3x1 matrix, so the matrix is actually the number of inputs by the number of outputs. So suppose we now extend this example and we make it a multi-class classification example, and it's very simple to do, because if we add a third fruit, we don't have more than 2 outputs, because we can either have a 1 and a 0 or a 1 and a -1 if we're dealing with bipolar. So in that case, your output vector is going to have a length of greater than 1. It has to be at least 2 in order to represent the output class. And you can choose any combination of 2 binary or bipolar values to represent the output class. So if we look at a grapefruit, we've now added on a third fruit in addition to the apple and the orange. So grapefruit is round, so its first value is 1. It has a rough texture, so its second attribute value is -1. And it's usually greater than 0.5 kg, so it has 1 as the last value. The 1 and 1 were just basically chosen randomly to represent the output. I could have chosen -1 and -1. I could have chosen -1 and 1 or 1 and -1. All you need to make sure is that the output for each class, the output vector for each class is different. So if you look at an orange, the attribute values are the same, but the output vector that we've chosen is -1 and 1. And similarly with an apple, we've got the input vector basically is the same, but now because we have 3 classes, we've got to have a different output vector. And the output vector is 1 and -1 here. So again, to visualize it, to see what our architecture looks like, the main difference here is now we have 2 outputs. So already our bias can't be one value. We need one value to map to each output. So that's B1 and B2. We now have 2 weights coming out of each input node, one going to each output. So we've got W11, W12, W21, W22, and W31 and W32. So if you look at the weight matrix, it looks different now. And similarly, if we look at the bias vector, it's also different. So the algorithm that we're going to look at in this lecture is the perceptron learning algorithm. The perceptron learning algorithm is essentially used to perform binary classification and solve linearly separable problems. So we don't usually have a multi-layer architecture for your perceptron learning algorithm. If your perceptron is a multi-layer neural network, then you have to change the algorithm that you're going to work with. Your learning algorithm can't be your perceptron learning algorithm. So the other types of algorithms that we're going to look at in tomorrow's lecture, we're going to look at the backpropagation learning algorithm, and that's commonly used for a multi-layered perceptron neural network. So the activation function used with the perceptron learning algorithm is the following. So if you've got binary representation, and if your n value is 1, your n value is 1, if your n value is greater than or equal to 0, your f of n value is 1. Similarly, if your n value is less than 0, then your f of n value is 0. The same thing for bipolar, but instead of outputting a 0, you're going to output a -1. And just a reminder of what your n value is. So m in that equation represents the number of inputs. And basically, you'll notice I've dropped the second value for the weights. I've just put down a WI instead of a WIJ, where J represents the output. Because if you're dealing with the perceptron learning algorithm, we know that we can only deal with binary classification. So there's always going to be one output. So there's no need to actually indicate that in the weight. So the weights are just being labeled based on the input. So basically, what you're doing is you're taking a weighted sum plus the bias of your inputs. So if we look at the algorithm now, the perceptron learning algorithm starts by choosing random values or zeros for your weights and bias. So that's the initial value. And we spoke about convergence before. So while there is still changes in your weights and bias value, they're being updated, which means that there's a difference between your target value in at least one of your instances in your training set and the output produced by the neural network. That means your algorithm hasn't converged. So while your algorithm's not converged, you're going to go through each element of your training set or instance in the training set. This for loop that you see here, the for loop actually represents an epoch because it's actually working through each one of your instances in your training set. So we're going to calculate f of n first, and then only if f of n is not equal to your target value for that training instance are you going to update your weights and your bias. So basically the way you update the weight is what it's the value it previously had, but then you're going to take a difference between the bias, the difference between the target value in your instance and the f of n, the activation of the neural network, and you're going to multiply that by the input value in your vector. Similarly, what the bias is going to be is its old value plus the difference between the target value in that instance of the problem in your data set and the activation of the neural network, which is f of n. So that data instance, for example, if you looked at the instances we just looked at now, it could be an apple or it could be the orange instance that we're looking at. Another version of the perceptron learning algorithm which you can implement is a version that actually includes something called a learning rate. And the learning rate is actually multiplied by the difference in the target value and the activation value f of n. And a common value used for the activation function, it could be 1 or it could be less than 1. Those are common values used. Similarly with your bias, when you're updating the bias and if you're using a learning rate, the difference between t and f of n will be multiplied by the learning rate as well. Okay, so now we've looked at the perceptron learning algorithm. I'm going to go back to the binary classification example that we looked at with the apples and the oranges, and we're going to look at how we can apply the learning perceptron algorithm to that example. So if you look at this example, you can see the weights are initialized to 0 and the bias is initialized to 0. So when we're calculating n, we've taken the first training instance represents your orange, and the input vector is 1, -1, and -1, which is P1, P2, and P3. We perform multiplication with the weight vector. So the 0, 0, 0, 0 there, that's basically W1, W2, and W3. And the 0 value that we're adding on is the bias. So when we do the calculation, we actually end up with the value of 0. And 0 is greater than, n is greater than or equal to 0. 0 is equal to 0, so our activation function will output a 1. But now if you look at the t value, the t value is -1. So we have a difference here. And as soon as you have a difference, then you've got to actually go and update the weights and bias. And the way you update the weights and bias is you use the learning rule, which we looked at in the algorithm, which changes the weights and changes the bias. So if we look at W1, W1 was originally given a value of 0. That was the random value it was given. -1 is the current t value, and we're subtracting 1 from that, and we're multiplying it by P1. So that gives us -2. Similarly, for the second weight value, it also had a value of 0. The difference remains the same because t is -1 minus 1, which is our f of n value in this case. And the only thing that differs now is that P2 is -1. So that will then give us a weight value of 2. Similarly, for W3, W3's weight original value was 0. The difference stays the same, and this time P3 is the same as P2. It's -1, and so that gives us a value of 2 as well. Now if we look at the bias is its old value plus the difference between t and f of n. So t is -1 in this case, and f of n is 1, so again we get -2. So now when we look at the next element of the training set, we use the updated weights and bias. We don't use the original one. So in this training set, we had 2 instances, one for an apple and one for an orange, which we've just looked at now. The next one is going to be for an apple, where the neural network has to learn the pattern of an apple. So now when we actually learn the new data instance from the training set, we use the updated weights and bias. So if we look at the second training instance, that now represents the apple, the vector that we came up with for the apple, and the output is 1 to represent an apple. And you can see now we're using the updated weights. So we've got -2, 2, and 2, and the updated bias, which is -2. If we perform the matrix multiplication and we add the -2, we get a value of -4, because we've got 1 times -2 plus 1 times 2, so both those values cancel off and give you 0. Plus -1 times 2, so that's going to be reduced to a scalar of -2, and we're adding -2 to that, so we get -4. So notice the way we actually do the multiplication, we're taking the inner product, so the dimensions on the inside must be the same. So if you look at the first vector as 1 by 3, and then the weight vector is a 3 by 1, and then that will give us a scalar which is a 1 by 1. Now if we look at minus 4 is actually less than 0, and for that reason our activation function outputs a minus 1. But our t value is 1, so again we have a difference, and because we have a difference we then go and update our weights and our bias again. So if we go and look at that now, that's our minus 4, and then our activation applied to that minus 4 is a minus 1. So if you look at the change of weights, the current weight value for W1 is minus 2. The value that the neural network output is a minus 1, and the activation that we want is 1. So t is 1, and we've got t minus minus 1 times 1. So both those values will then give you an output of 0. We then look at the next one, W2. We've got 2 into 1 minus minus 1. That cancels off, and then you end up with the value of 2, which is going to give you a sum of 4. And then if we look at the last one, you've got 2 plus 1. That cancels off, which gives you a 2, but then you've got a minus 1. And then if you multiply that through, you're going to get a value of 0. Similarly with your bias, you've got 0 into 1 minus 1, which is going to give you an output of 0. So our weights are now updated, and we're now on the second epoch. Second epoch meaning we're going to go through the training instances again, one instance at a time. So if you look at the first instance, that represents the orange. And if you look at our updated weight value, so we've got 1 times 0 plus minus 1 times 4 plus minus 1 times 0, which is going to give us minus 4. Our bias is 0, so we get an output of minus 4. That's less than 0. And if we apply the activation function to that, we're going to get a minus 1. If we look at the next element in our training set, there's no change to the weights and bias because your t values are the same as your f of n value. So your t value for the previous training instance was minus 1, and your f of n value is also minus 1. So for that reason, we don't change the weights and the bias. We use the same weights and bias. We move to the next element of the training set, or the next instance. So you've got 1 times 0 plus 1 times 4 times minus 1 times 0, which is going to give you a 4, plus the bias, which is 0. So your output is going to be a 4, and if you apply the activation function to that, 4 is greater than 0, so you're going to get an output of 1. So if we look at t in our current training set, and if we look at our value for f of n, they're both exactly the same, and because they're exactly the same, then we don't change the weights. There's no need to change the weights or the bias in this case. So far we've been looking at the single layered neural network for the perceptron learning algorithm, but this has limitations and it probably won't be able to solve most real world problems. For that reason, we need to then look at the multi-layered neural network, a perceptron neural network. That would be able to do things like perform multi-class classification, etc. So the algorithm we looked at is restricted to the single layer neural network. So your perceptron learning algorithm can only be used for a single layer perceptron neural network. If you want to use a multi-layer network, we've got to look at other algorithms. Now there are a number of different algorithms you can use. You can use gradient descent, you can use stochastic gradient descent. The one that we're going to look at, which is quite a versatile algorithm, and it's not only used for classification, it can only be used for other things, is the backpropagation learning algorithm. And as its name suggests, it propagates values back through the neural network based on the output it gets. And that's what we're going to look at in the next lecture.